The first thing in this lesson, I would like to start with the real gas. So basically, a real gas acts as an ideal gas under the STP condition. What's this STP condition? It's the standard temperature and pressure, which means that under a pressure of 1 atmosphere, basically it's a bit higher than this, which is approximately 1.01 times 10 to the power of 5 Pascal, or under the temperature, which is the 0 degrees Celsius, which is the 273 degree Kelvin. So we say that a real gas, it acts like an ideal gas under low pressure, high temperature. We can say under low density as well. Now, what is the kinetic model of an ideal gas? What are the assumptions that usually we consider for a gas to be an ideal? I'm going to list some. Usually these assumptions, they come in paper 2 or sometimes in paper 1 as well. So it's important to memorize and understand, of course, all of them. So the assumptions that I'm going to write are the following. The first assumption for the gas to act as an ideal gas is that the molecules are considered to be point particles of neglected volume. So let me write this. So the first thing is that the molecules of the gas are considered to be particles. So are particles of neglected volume, or in another word, the volume of the particle, it's neglected with respect to the volume of the gas it occupies. The second thing that you need to know, the second assumption is that no intermolecular forces between these molecules. So no intermolecular forces between molecules of an ideal gas, which means that, in another word, that the potential energy of the gas is zero. The third thing that you need to know is that the particles are always in motion and they obey the law of mechanics, so they are always in motion, okay, and they obey laws of mechanics. The fourth thing is that if these particles collide, okay, so of course there's no forces between the molecules, but when there is a collision, there will be forces. But the type of collision is going to be elastic. So when they collide, the collision is elastic. And from the momentum video, we know that when the collision is elastic, the kinetic energy is conserved, which means that as time passes, the temperature is not going to change, because we know that the kinetic energy is proportional, or the average kinetic energy is proportional to the temperature. So as time passes, the temperature of the gas is not going to change unless there is an external factor acting on this gas. Okay, so we can say that the internal energy of the ideal gas, it's only equal to the kinetic energy, and we're going to talk about this later. Basically, it's going to be equal to the number of particles of the gas times the average kinetic energy of one particle. And I'm going to discuss this later in another video on its own, because there's some derivation that need to be done here. The fifth thing that you need to know is that the particles are identical, which means that they have the same mass. Okay, and what else? Basically, that's it. Okay, so these are the assumptions of an ideal gas. Now, when the gas is considered as an ideal gas, this means that it obeys the ideal gas law. Okay, so you need to know that ideal gas. Okay, so ideal gas obey the ideal gas law, which means that I can use this relationship. So when the gas is considered to be an ideal, I will be able to use this ideal gas law, which is the PV equal nRT. Now, what's the P? Let me define each physical quantity. This P, it's the pressure. And we know that pressure is the force applied per unit area, which means that the unit of pressure is Newton over meter squared, but this unit, it has another name, which is the Pascal. So every 1 Pascal is equivalent to 1 Newton per meter squared. The second thing that you need to know, so this is the pressure of the gas, V is the volume occupied by the gas. Actually, it's the volume, the free volume that the gas can move in. It's equal the unit is meter cubed. R, it's the ideal gas constant. It's in your data booklet. It's equal to 8.31 joules per Kelvin per mole. This is in your data booklet. T, it's the temperature of the gas. It should be in Kelvin. Okay, so here you have to convert to Kelvin if you are using this equation. And the last thing, which is N, that I'm going to talk about it more here, which is the number of moles. The unit of N is mole, and I'm going to discuss N further. So let me discuss a bit the meaning of a mole. Okay, so whenever I say 1 mole of something, I mean that this thing, it contains an amount of particles equal to the same amount of particles as there is in 12 grams of carbon-12 neutral atoms. So let me write this. This is the definition of a mole. So a mole, it's basically it's an amount of substance that has an equal, so it has equal amount of substance as in 12 grams of carbon-12. So this is an isotope basically of carbon-12 neutral atom. So if I bring, in another word, if I bring a 12 grams of a carbon-12 atom, it will contain an amount of particles equal to 1 mole. Okay, so if I have a 1 mole of something, it will be equal to 1 mole of anything else, because this is the quantity. Okay, now this number of mole, it's equivalent to the number of particles over the Avogadro's number. So this is basically, it's the number of particles. It can be the number of atoms, it can be the number of molecules, it's the number of entities, okay? And this Na, this is the Avogadro's number, and it has a constant value. It's in your data booklet as well. It's equal to, this Avogadro's number is equal to, so Na, 6.02 times 10 to the power of 23, and the unit is, if this is particle, if N is particle, it's going to be particle per mole. If N is atom, then it's going to be atom per mole, okay? So this is the unit of the Avogadro's number, but also the number of mole, I can find it by dividing the mass over the molar mass. But there's something very important here, that the mass needs to be in gram. So this mass, it needs to be in gram. Why is this? Because the molar mass, it's in gram per mole. So this is in gram per mole. And if you want to find the molar mass of any substance, it's equivalent to the mass number. So the same number, which is the mass number, but in grams per mole. And what I mean by this, I mean that, for example, if you have a helium, okay, so this is the helium atom, the molar mass of helium, it's equal to 4, which is the mass number, but in grams per mole. If I have, for example, like water molecule. So the molar mass of water molecule, it is 2 times the mass number of a hydrogen plus that of oxygen, which is the 16, the mass number of an oxygen. Okay, so it's going to be equal to 18 grams per mole, and so on. Okay, so basically this is the equation that I'm going to use in solving any question regarding the number of moles or the molar mass, all of these things. Okay, so this is very helpful. Let's check how we're going to solve this. So I'm going to give you some example on this. 2 of them are from the Tsoukas book, which is the Cambridge one, and one paper 1 question. And there's a lot of paper 1 questions that you can solve on your own. So here he's saying estimate the number of atoms. So he wants the number of atoms of gold in 1 kilogram. So I have to convert this to gram of gold. Since he has given you the notation of gold, so this is the molar mass. In order to find N, so N over the molar, the Avogadro's number, it's equal to the mass over the molar mass. Okay, so I'm using this part of the equation, which means that in order to find how many atoms is in 1 kilogram of gold, all what I need to do is to find this ratio and multiply it by Avogadro's number, which means that this mass, it needs to be 1000 grams. Why I need to convert it to grams? Because this is the gram per mole times the Avogadro's number. Okay, so if you make this on a calculator, let me just make it very quickly. So 1000 divided by 197 times 6.02 times 10 to the power of 23, and the answer is going to be equal to, I made a mistake, so 1000 divided by 197 times 6.02 times 10 to the power of 23. So the answer is going to be equal to 3.05 or 06 times 10 to the power of 24 atom per, basically it's atom. So this is the amount of atom of gold in 1 kilogram of gold, okay? So every 1 kilogram of gold, it contains this much of atoms in it, atoms of gold, of course. Now the second question, he's saying calculate how many grams of scandium contain the same number. So this is a bit different type of question. So here I have the molar mass of scandium, okay? And he wants how many grams, which means the mass of scandium contain the same number of molecule as 8 grams. So this is the mass of argon. And given the molar mass of argon. What was the condition that he said? He said that the number of molecules of scandium is equal to the number of molecules of argon. So this is the condition that he stated. So how many grams of scandium I should bring such that these two have the same number of molecules as, of course, in 8 grams of argon. Okay, so what is the mass so that it has an equivalent number of molecules as in 8 grams of argon? So in order to do this, all what you have to do is that you can replace the number of molecules of scandium by the mass of scandium over the molar mass of scandium times the Avogadro's number. And why I'm doing this? Because this is how I find the number of atoms. Okay, so I found it from this equation basically. This is equivalent to the mass of argon over the molar mass of argon times Avogadro's number. So basically this is going to be crossed over. And then I'm going to cross multiply so that I'm finding the mass of scandium in such a way that I'm multiplying it by the ratio of these masses. Okay, so all what you have to do is to put the mass of argon in grams over the molar mass of argon times the molar mass of scandium, and you will end up having the following. So let me do this quickly. So it's 8 times 45 divided by 40, and the answer is 9. What does this mean? It means that if I wrote 9 grams of scandium and 8 grams of argon, they will be having the same number of molecules, okay, in this case. One more last question. Try doing it on your own. So he's saying a container hold 20 grams of argon. So this is the mass of argon, and this is the molar mass of argon. And 40 grams of neon, and this is the molar mass of neon. What is the number of atoms of neon? So he wants of argon over the number of atoms of neon. So simply, I'm going to use this ratio. Remember, N over Na, it's equal to M over M. So I'm always using this part of this relationship. So I need to put M of argon over molar mass of argon over the mass of neon over the molar mass of neon. I canceled out the Avogadro's number. So this part is going to flip, and it's going to be equal to the mass of argon over molar mass of argon times the molar mass of neon over the mass of neon. And all that I need to do is to just substitute. So it's going to be 20 over 40 times 20 over 40. Okay, so I'm going to cancel out these zeros. And this 4 with these two 2's, so I'm going to end up having 1 over 4, which is 0.25. So that's it. This is regarding the number of moles, regarding using this equation. Okay, of course you can, what you can do is that you can first find the number of mole, and then the number of mole of anything is equal to the number of mole of anything else. But usually I like to use this equation as I have shown you here. Now I'm going to move to something else. Before moving into the thermal processes, I need to say something about the ideal gas law here. So this PV equal nRT, I can write it as, if I replace N by N over Na, which is the number of atoms over the Avogadro's number, then this can be written as such. And this ratio right here, this has a name in physics. It's called the Boltzmann constant, and you can find the Boltzmann constant in your data booklet. So it's NKBT. So this is another way of writing the ideal gas law, where KB is the Boltzmann constant and N is the number of particles or atoms or molecules. So this KB, Boltzmann constant, it's in your data booklet, okay? Now let's go to talking about the thermal processes. So we're going to talk about some gas laws. So consider I have a container right here. Let's say that this container, it has a certain number of gas molecules. So there's a certain number of moles, and the temperature is T1. The pressure of the gas is P1, and the volume initially is V1. So let's say that I'm heating this container in such a way that this lid here, it's fixed. So if it's a fixed lid that it can't move, this means that this process, it's called the isochoric process. So it's a process which is happening in such a way that the volume is constant. So here, the first process, I'm going to call it the isochoric process, which is the constant volume process. So after some time, what will happen is that the volume is going to remain constant. The number of mole is still the same because it's a closed container, but the pressure is going to increase and the temperature is going to increase. Okay, so if I use the ideal gas law, which is the PV equal nRT, you can notice that the ratio, which is P over T, which I can write it as NR over V, it's always constant. And why it's always constant? Because these are always constant. So here, number of mole, R and V are constant, which means that P over T at any time is always constant. Okay, so I can write here that P1 over T1 is equal to the P2 over T2, and if I continue heating more, so it's equal to P3 over T3, and so on. So this law right here, it's called the Gay-Lussac law or the gas third law. Okay, I can explain what's happening or the relationship between the pressure and the temperature by simply plotting. So if I plot in this case the pressure versus the temperature graph, but let's say that the temperature is in Kelvin, so this means that, look at this relationship. So this means that if I write it as P equal NR over VT, okay, so I'm on the y-axis, there's the pressure, and on the x-axis, there's the temperature. So this means that the relationship is going to be a proportional relationship where the slope is equal to NR over V. And that's it. Now, there's something that I would like to say, which is if this process is taking place at a higher volume, then this means that the slope will decrease, so the graph will shift something in this direction. Okay, so it will be lower and lower and lower. Now, if I'm plotting the pressure versus the temperature, but the temperature is in degrees Celsius, so here you have to pay attention to something, which is that the graph will look something like this. So this is the pressure here in Pascal, and this is the temperature in Celsius, where this intercept is the minus 273 degrees Celsius. But of course, the slope is still going to remain the same, okay? And of course, for a higher volume, the graph will shift in this direction. So it will shift in this direction and so on. Now let's go to another thermal process. Let's say in this case, this lid here, it's free to move. Okay, and I'm heating this container. Okay, so in this case, if I started with N1, P1, V1, and T1, after some time, what will happen is that the number of mole is going to remain the same, but the pressure as well is going to be the same, because as I'm heating it, the lid is going to go higher and higher, okay? And the volume is going to change, it's going to become bigger, and the temperature is going to increase. So basically, this process, it's called the isobaric, so constant pressure, isobaric process. So here the pressure is constant. So if I would like to use the ideal gas equation to see the relationship between the pressure and the volume and the temperature, so in this case, PV equal nRT, P is constant, so V equal nR over P over T, this is equal to constant. And why is this? Because this ratio is constant, which means that at any time, at any instant, V1 over T1 is always going to be equal to V2 over T2 and V3 over T3 if I kept on heating and so on. So basically this law right here, if you look at this law, it's called the Charles law. So this is Charles law. And if I'm plotting, look here, if I'm plotting the volume versus the temperature, so the volume on the y-axis and the temperature on the x-axis, so the relationship is going to be linear with a slope m, which is equal to nr over p. So here, the same thing goes here. If I'm plotting the pressure in Pascal with the temperature in Kelvin, the relationship is going to look as before, with the slope in this time, it's equal to nr over p. And for a higher pressure, of course, the graph will shift downward. And if I'm plotting the graph with a degree Celsius, so the graph is going to shift in such a way that the intercept is going to be minus 273. So it will look something like this. So this is minus 273 degrees Celsius. Okay. One more, actually two more processes. So this is going to be the isothermal process. So how am I going to have an isothermal process? Let me just write it, isothermal process. So this is, I'm modeling the gas in such a way that the temperature is kept constant. So how can I do this? If I apply a force on this container, but this force is being applied in a slow rate. So after some time, of course, the volume is going to decrease and the pressure is going to increase, but that temperature is going to remain the same. Okay, so here if I started with P1, V1, T1, N1, after some time, it's going to become P2, V2, T1, and N1. So in this case, so I said that the temperature is constant, which means that so here P1 V1 is going to be equal to P2 V2, and why is this? Because PV equal nRT is constant, because N, R, and T are constant. So this law right here, this one is called the Boyle's law. So if I'm going to plot right here, if I'm going to plot the P versus the 1 over V, so this is on the y-axis, slope, and 1 over V is on the x-axis. In this case, the graph will look something like this. Actually, it's not meter cube, I'm sorry, it's 1 over V, so it's meter cube, it's per meter cube, so it's m minus 3. Okay, and the graph will look like this, where the slope is nRT. So for a higher temperature, the graph will shift in this direction. So always try to analyze what's happening to the slope. Now, if on the other hand, I'm plotting P versus V, so now it's not going to be a linear relationship. It's going to be like a hyperbolic relationship. So it's going to look like this because it's 1 over x. So the relation is 1 over x. Okay. Now, if I'm doing this with a greater temperature, the graph is going to shift in this direction, which means that the graph will be something like this. It will move like this and so on. So this is Boyle's law. One more thing now, if I'm applying the force, but this force is a fast force, so in this case, the temperature and the pressure and the volume are going to increase. So after some time, T2, P2, V2, and N2, so of course, actually it's N1. So here I'm changing the volume, the pressure is going to increase, and this is N1. So in this case, I can write that P1 V1 over T1 is equal to P2 V2 over T2, and it's equal to NR, which is constant. So basically, this is called the general gas law. And of course, there's no any drawing for this because here there's 3 physical quantities that are changing. And that's it. So these are the different thermal processes. We still have to solve some examples on that.